Okay, into the third subtopic for the nuclear models and radioactivity topic, and that's radioactive half-life. And in this video, we're going to explore radioactive half-life, really some of the mathematics of radioactive decay, if you like, but at not too complex a level. And then we're also going to look at some of the implications for the storage and disposal of nuclear waste. Let's get into it. So firstly, if you haven't already, make sure you check out this video here. Half-life radioactivity physics fuse school gives a really good simple explanation and a really good graphic explanation of radioactive decay and half-life. So firstly, what do we need to know? The number of radioactive nuclei in a sample of a given isotope decreases exponentially with time. So the idea that when we have a radioactive sample, the number of nuclei that are present, the number of radioactive nuclei that are present, basically undergoes exponential decay, which looks a bit like this red line here. Now, hopefully you've seen exponential decay before somewhere, but if you haven't, don't stress too much. I think you'll pick it up fairly fast. So the key quantity, the key parameter, whatever you want to call it, that we use to describe radioactive decay is the half-life. And the half-life is the time it takes for half the sample to decay. So in this case, to go from 100 radioactive isotopes to 50 radioactive isotopes, that is one half-life. Or the time that it takes to go from 50 to 25, from a half to a quarter radioisotopes. And the key thing about exponential decay is that time is always constant. So the time it takes for the number of radioactive isotopes to decay to half their original amount is always constant, regardless of how many you're starting with. So the time to go from 200 to 100 is the same as the time to go from 100 to 50 is the same as the time to go from 50 to 25. And we call that time the half-life, and we often give that the symbol T with a little subscript half for half-life. Now, what's also important about this quantity, this half-life, is it is constant. And when I say that, half-life is independent of the physical state, whether it's solid, liquid or gas, or what temperature it's at, and the chemical state, i.e. what other atoms it's bonded to. So this half-life will be the same regardless of the physical or chemical state of the isotopes. The other factor that we need to know is the activity. So let's firstly talk about what do we mean by activity. Activity, maybe I should put an arrow here for this. Activity is basically the number of decays per unit time, and the typical unit we use is the becquerel, which means 1 decay per second. So we can normally, if we are measuring a radioactive sample, we can't go in there and count, like I know in this example here that I've got, we could sort of count the number of isotopes and then count them again. But in reality, we can't go and count atoms in a sample. What we can measure is the amount of decays that are happening each second by using something that can detect the radioactive particles, the alpha and the beta and the gamma that are emitted. So the activity, the number of decays, is proportional to the number of radioactive nuclei present. Therefore, activity decreases at the same rate as the number of nuclei. Both decay exponentially at the same rate. So this curve here for decay looks the same whether you think about the number of atoms that are present or the activity, the number of decays that are happening each second, because the number of the activity, the number of decays is proportional to the number of atoms. The more atoms that are present, the more decays. The less atoms that are present, the less decays. So we can consider these almost the same, and analyse it whether we have the activity, which is more likely what we can measure, or the amount of sample, which is probably a little bit easier to picture, at least to start with. That's what these sort of cartoon figures here are indicating. So we've covered that first part there. So you need to be able to use data to estimate the half-life of a radioactive nuclei. So let's just say we knew you had a sample here, and let's say we knew it had an initial, we could do activity or amount, so it doesn't matter. So we knew it had an initial activity of, doesn't really matter. Let's go initial activity of, say, 400 becquerel. And then we knew at some time later it had an activity of 100 becquerel. And let's say we knew that time there was, doesn't really matter, 4 days. And you'll always get fairly simple numbers in these. I'll go through an example in a minute. You could say, well, what would the half-life be? Well, it went from 400 to 100, so 400 to 200 would be one half-life. 200 to 100 would be a second half-life. So that's 2 half-lives. That took 4 days, so the half-life in that case would have been 2 days. So basically just using that data and those curves to work that out, and I'm going to do an example in a sec. Again, you could do the exact same thing for the number of samples. So if we know there was 100 atoms present, and then later on we knew there was 25, we could use that same process. More interestingly and more importantly is they often use this technique to do radioactive dating. So they use things like carbon-14, which is a radioactive isotope that's present in our atmosphere. I think it talked about that in one of the videos. I might put a video up on it if it doesn't. And if we know, for basically natural processes where radiation strikes the top of our atmosphere, keeps making carbon-14 at a constant level in our atmosphere, and we're breathing in and taking in carbon. Well, not breathing in, but we're taking in carbon through our diet. So we know how much radioactive carbon is present in a living sample, but once you die and stop absorbing carbon, by looking at the amount of carbon-14 that's left, you're able to work out how long since something died. They do a similar thing with rocks and a uranium-238 isotope, which has a half-life of like 4.5 billion years. It's a very, very long-lasting one. And it basically, by looking at the amount of uranium-238 left in rocks, we can get an indication of the age of the rocks. We'll probably do some questions on that as well as we go. Just for those of you who are more mathematical, and if you're not mathematical, don't worry about this bit, but this graph we can describe mathematically using this formula here. N, which is the amount of, or it's the activity, it doesn't matter. N0 is the initial amount, times by half to the power of n, where n is the number of half-lives, and we can work that out from going t divided by the half-life. So in this case here, 4 days, the half-life was 2 days, that would be 2 half-lives. And that can give us basically a mathematical formula to calculate these and describe them. But you don't need this to use this formula. I'll show you when we do the example, the approach that I would normally use. But if you are someone who's really strong in mathematics, you might like to know about this, and you might even be more comfortable with this method. But, basically this formula tells us if we start off half to the power of 1 half-life, we have half the amount left. So we go from 1 to the half. After 2 half-lives, half to the n, half squared would be a quarter. After 3 half-lives, 2 to the power 3 is 8, so we would have an 1/8 left. After 4 half-lives, we'd have a 1/16 left. So that basically formula just more mathematically says what I just described there. Okay, let's go. I think I've covered everything there. Let's go and do an example. So this is an old exam question. It's probably as hard as a question gets, but I don't think it's that hard. So let's read through it. A radioactive source containing 8.5 times 10 to the minus 6 kilograms of cesium-137 initially has an activity of 2.72 times 10 to the 10 becquerel. The source is effective until its activity decreases to 6.8 times 10 to the 9 becquerel. Cesium-137 has a half-life of 30 years. Calculate the mass of cesium-137 in the source when it stops being effective. So I like this question because it has the activity, it has the amount, it has some simple half-life calculations in it. So this is the process I would usually use for these. You could go back to that mathematical formula, but I think that's probably unnecessary unless you want to show off your mathematical genius. So the initial activity was 2.72 times 10 to the 10 becquerels. Now, after one half-life, so after 1 times a half-life, which in this case would be 30 years, that would fall to half that amount, which would be 1.36 times 10 to the 10, times 10 to the 10 becquerel. So you can see there we haven't got down to 6.8 yet, but if we keep going, and as I said, you'll only get these questions where it's basically works out simply like a whole number of half-lives. So after another half-life, so after another 30 years, that will drop by half again, and half of 1.36 is 0.68, but we just go down to if we did this in the calculator, we would divide that by 2, we would get 6.8 times 10 to the 9 becquerels. So you can see there, that's the level where it's no longer effective. So that has taken 2 half-lives. Could have used the T half symbol there, all right, 2 half-lives, which is basically 2 times 30, which is equal to 60 years. Not that we even need to know that it's 60 years, we really only need to know it's 2 half-lives, because we want to know after 2 half-lives, what's the mass of cesium-137 that would be present. So we would go 8.5 times 10 to the minus 6, and then if we divide that by 2, we will get that's equal to 4.25 times 10 to the minus 6 kilograms. So that's after 1 half-life, 1 times a half-life. So then we got to, again, going to go down here, divide that by 2 again, and we will get 2.125 times 10 to the minus 6 kilograms. That's after 2 half-lives, which is what it took to get to that activity. Now, strictly speaking, we only get things to 3 significant figures in the question. So we should only have 3 significant figures in our answer. That's a 5, so that rounds up. So we should say 2.13. The 2 rounds up to a 3 because the 5 is there. So that's a typical half-life type question. Hopefully that was, you could follow that along. If not, though, we'll do some more examples and get some practice at it, and hopefully you'll become proficient at that quite quickly. Let's move on. So the final thing we need to consider is the basically storage and disposal of the nuclear waste. So the range of products of some with long half-lives, means that nuclear waste must be stored for long periods. Explain the requirements for the safe storage of waste. Now, I'm not going to really talk in huge detail about this. This is one I actually want you to more go and research for yourself. There's a video on safely managing radioactive waste here that I would like you to have a look at. And finally, I think that video is produced by ANSTO. And ANSTO also have a really good website talking about managing nuclear waste in Australia. This is obviously an issue that has a local significance for us on EP. And I've just pulled out this flowchart. This sort of shows, the most common place that we get radioactive waste from in Australia is in our hospitals for medical use. Often that just goes into short-term storage until it decays to safe level and it just goes out with the regular rubbish. Sometimes, same with other low-level waste, let it decay to a level and then it can just go into regular waste disposal. Sometimes we get some intermediate level waste. That then needs to go at the moment that's stored at Lucas Heights, which is in the suburbs of Sydney, where Australia's nuclear reactor that makes most of these isotopes for medical use is. They also produce some high level waste here. It doesn't say that, but this spent fuel is high level. That gets sent overseas for reprocessing and then gets sent back to Australia. You'll see that talked about in one of these videos as intermediate waste. And what they're looking for is to build a long-term storage facility somewhere in Australia to store this intermediate waste. And some of you may be aware that the place that they're looking to do that there, which has been in the news a lot lately, is at a spot near Kimber in South Australia at the top of the Eyre Peninsula. So there is a great local context to this issue. So please watch the video, have a look on that website. This may be, it doesn't have to be, but this may be an excellent source for you to, an excellent issue to look at for your SHE investigation task. Remember, if you like this video, click like below and don't forget to subscribe to my channel. Cheers.